Some stars should not exist, and yet we have found them. They bend physics and force us to rethink dense matter. A tiny pinprick of light sits, denser than an atomic nucleus. Strange stars are objects made of exotic particles. So strange stars might be real, and they upend our assumptions. Net result, this video shows why they matter. A star the size of a city glows like molten metal. A strange star is a compact star made of deconfined quarks. This matters because it challenges our models of matter at extreme density. When gravity compresses a neutron star core, neutrons break down. Quarks escape their neutron cages and form a new soup of matter. Strange quark matter can be more stable under some theories. A strange star might weigh twice our Sun, in 10 kilometers. Astronomers suspect a few objects with radius around 6 kilometers. So strange stars are dense, exotic, and potentially stable alternatives. Bottom line, the concept reshapes what a star can be. A collapsing star screams inward, layers peeling like an onion. Formation can follow a supernova or accretion-induced collapse. This matters because the collapse path decides which exotic phases appear. At extreme pressure, nucleons overlap and quarks roam free. A phase transition can release energy and alter the star's radius. Magnetic fields and rotation change thresholds, making formation trickier. Simulations show conversion fronts sweeping outward in milliseconds. Some models predict a final radius near 8 kilometers, so violent collapse can seed exotic cores under the right conditions. To recap, the birth is violent, and small differences decide the outcome. Inside, particle densities climb beyond anything on Earth. Strange matter mixes up to 3 quark flavors, including strange quarks. This matters because whether strange matter is more stable changes cosmic end states. Quantum chromodynamics predicts binding energies under extreme density. If energy per baryon drops, the state becomes globally favored. Surface tension and charge separate phases, complicating stability calculations. Calculations vary, giving stability windows across pressure and composition. Some estimates place stable strange matter above 3 times nuclear density, so stability is uncertain, and tests require astrophysical evidence. In short, theory leaves room for strange stars, but not certainty. Detectors listen to pulses like cosmic metronomes in space. Signatures are measurable effects on light, neutrinos, and gravity. This matters because finding one would confirm exotic matter beyond theory. A strange star's radius changes pulse timing and spectral lines. A sudden conversion could emit a neutrino burst and gravitational waves. X-ray cooling curves differ because heat capacity changes with composition. NICER observed pulsars with radii hinting at unusually small sizes near 10 kilometers. LIGO might catch a conversion wave if conversion is violent and asymmetric. So instruments can spot telltale changes if we know what to look for. Net result, multi-messenger eyes are essential. Astronomers sift through catalogs hunting oddballs in the data. Candidates are compact stars with unusual radii or cooling patterns. This matters because proving a candidate would rewrite stellar evolution narratives. We compare mass and radius using light curves and pulse timing. Cooling faster than expected points to enhanced neutrino emission or different cores. Glitches and magnetic behavior can also hint at an exotic interior. Some X-ray sources show radii estimates under 8 kilometers, puzzling researchers. A handful of pulsars display cooling curves inconsistent with neutron star models. So there are intriguing candidates, but none prove exotic matter yet. Bottom line, clues exist, but proof remains elusive. If strange matter is stable, it changes how stars die across the universe. A single conversion could turn a neutron star into strange matter. This matters because that outcome affects supernova remnants and galactic chemical evolution. Strange stars might eject less heavy elements, altering chemical yields over time. If contagion occurs, strange matter could seed conversions across binaries. A binary partner could be converted, changing gravitational wave signatures dramatically. Models show conversion altering peak frequencies by tens of hertz. So cosmic processes and observations would shift if stability holds. What to remember, stable strange matter would rewrite many astrophysical stories. In chalkboard rooms, theorists push equations toward extreme limits. Testing relies on nuclear experiments and heavy ion collisions on Earth. This matters because lab constraints narrow viable exotic possibilities. Particle accelerators recreate high densities, short-lived in collisions. Lattice QCD and many-body theory compute pressures and binding energies. Combining theory, lab, and astronomy narrows viable models steadily. Heavy ion experiments reach densities near nuclear saturation briefly. Recent lattice results hint at softer equations at high temperature, not density. So lab and theory together tighten the net around strange matter. Net effect progress is incremental, but steady. Remember, stars that should not exist might actually be out there. If you liked this deep dive, subscribe for more curious science. Final thought, detection would change our view of matter forever.